Well, thank you very much for being here. Thank you, Daniel, for the introduction. I was saying thank also my team at the University of Calgary for allowing me to represent this work here, led by Dr. Ian Purcell. So I'm just going to dive right in. So provenance is one of the most important pillars in reproducible science. It is essential in safeguarding scientific integrity. The what was done, how was done, are probably the most frequent questions posed every time we're performing a study or in a collaborative environment. So capturing and managing and utilizing provenance in provenance-centric workflows enables users to see not only the what was done and how, but also when, by whom, and what inputs were used, and what output was generated. So what we have been doing is that we have using DataLad project for data management and to generate usable and shareable provenance for our scientific workflows. For those of you who are a bit less familiar with DataLad is just a wrapper tool around Git and Git Annex that performs data management and provenance recording. It is a great tool to create reproducible and auditable data pipelines. We can share an entire scientific project and its provenance with just a simple Git clone. So when we come to computing these workflows in remote infrastructure, we look at Globus Compute to schedule these computations. So what we have been doing in the past year is develop a small scheduler system that uses retrospective provenance generated by DataLad to control the execution pathways of the scientific workflow. So this is what we're trying to do. We have a graph that describes how the workflow is going to flow. We have some empty provenance because nothing has been executed. So if the first task or process is runs, generates a file, and that generates some provenance. And now from this state of this graph, if I compare the actual graph that has been realized with the original one, I can see and say, okay, well, process 2 needs to be scheduled now. And that gets sent to Globus Compute, and then it goes on and on until the entire workflow is complete. So this is another view of what is happening behind the curtain. So we compare on the client the DAG that is represented as an abstract graph along with the concrete graph derived from provenance. The root nodes of the difference between the two graphs then are scheduled for execution, and it's just an iterative process that repeats itself. So one of the things we stumbled upon is that we had issues with Globus Compute was that there are some limits in the data transfer sizes. So we had to develop a sort of a framework around it to get around this 10 megabytes limitations on sending data from the client to the endpoint. So this is how we address this thing. We create two repos. One resides on the client system. So these are two DataLad repos, I should say. One resides on the client system, which is also orchestrating the workflow execution. The second one is located at the remote endpoint. And these are just represented by small databases here in this image. Once a task is completed, then one repo is one step ahead in the remote system. What it does is automatically creates a Git bundle, and that Git bundle is transferred back with the Globus Transfers, and then it's imported in the client system, and then we can process to reconstruct the provenance graph and then determine what the next task to be scheduled next and submitted. It works. It's a very hacky solution. Probably the best way to do this, but it's a very interesting use case of Globus. So we attempt at having a Globus Compute compatible provenance-centric workflow management system that allows to deploy these workflows with secure remote infrastructure and endpoints using Globus Compute. And we can apply a combination of Globus Transfers and DataLad updates to reconstruct this retrospective provenance updates, allowing the workflow manager to do the DAG and schedule new tasks.